As Jamie said, I work for Mega now. It's a good company, challenging but fulfilling at the same time. But I also say that it is good to be home to Cardiff University, where I started my professional career. I'll say a few words about what Mega is, what do we do, and what are the links between Mega and Cardiff University. Then I'll move on to the main topic of our discussion today, which is the current transformers, the design principles, the performance requirements, but also not only related to magnetics, but also to other problems which have to be solved with making current transformers. And there will be a number of applications with just regular clamp type current transformers, but also some testing of these. Okay, what is Mega? How it all started? There was a gentleman called Sidney Evershed who in 1899 invented a hand dynamo, which basically would have to be hand cranked, but was generating voltages high enough to permit insulation testing. And these initially were two separate instruments. One was high voltage dynamo to generate these high voltages, and there was an ohmmeter to measure the state of the insulation. These were later combined, and the one you see now from 1922, that was the first device which was integrated into a single device. So with one hand, someone had to hold it, with the other one, turn the handle, and then the answer was coming on the screen, which was pretty impressive 100 years ago. And because this was what the device really did, it measures resistance in mega ohms. So it was called mega ohm meter, hence using beginning and end of these two words, the word mega was made. And it was registered as a trademark in 1903. So as you can see, this was more than 100 years ago. And the company initially was Evershed and Vignolles Limited. And that was the beginning of the name Mega and the company. Since then, there were a number of changes, a number of different names involved. Obviously, the insulation testers are still the very basis of Mega, and what this thing might look like today is this. It's obviously battery operated and an electronic digital display, but it performs the same role as it did 100 years ago. It measures insulation of various devices. Another very big part of Mega is AVO. Again, quite a few years ago, a post office engineer, Donald McKeddy, came up with the idea that instead of carrying different instruments for measuring resistance and for measuring current and for measuring voltage, he managed to combine all of them in a single one. And this device could measure amps, volts, and ohms. Hence, using just the first letters, the word AVO was conceived, and that was manufactured for over 50 years. We only stopped making it in 2008 because that was a mechanical device, and we could not buy the parts we had. No one ever, people just stopped supplying the parts because there was just not too much demand for it, and the precision required, it was impossible to make this anymore because the demand was still there. Customers liked them so much, they still wanted to buy them. And this model you see here is one of the last one manufactured. So the company was named AVO Limited for quite some time, and in '87 the name was changed sort of back to Mega, and there were various other names involved. I won't bore you with details. Today the company is called actually Mega Instruments Limited, and is part of a Mega Group. We have 4 manufacturing sites. You see the map of the world here with the red names on it. The red names denote the manufacturing sites. There's one in the United Kingdom in Dover. This is our site. There's one in Sweden in Täby, and there are 2 in the United States, Daliforge and Dallas. These 4 manufacturing sites, they manufacture products from roughly 3 sort of types of equipment. Is for power, for building and wiring, and for telecommunications. In total, including the sales channels, we employ about 1,500 people. these are sort of a bit more groups of products which are made. I mean, some of them you see on the poster there as well. About 25 main groups. Depends how you really look at each category. The ones marked in red, these are sort of the closest I could think of which immediately employ current transformers, which is obviously the topic of our meeting today. But of course, in most of them, there are electronic current transformers for detecting the currents being involved, or for protection, or for any other reason. So examples of some of these I'll show today, and these would be for power quality instruments, for ground resistor testers, and for multimeters. This is an example of just a few products Megger does, just to give you some idea of the range of the things. To start with, that's a clamp-on current transformer, which I have a sample of here. You'll be able to look at it later. Obviously, as I mentioned before, insulation testers is a quite big chunk of what Megger does and what Megger is famous for. And these devices, they can measure insulation up to tera-ohms. It's an incredibly high number. At the opposite end of the scale, we also do low resistance meters, and these can measure down to micro-ohms. So you can see the scale from micro to tera. It's just massive. There are transformer turns ratio testers, and these are specifically designed to work with power transformers. The big piece of equipment you see there, that's actually specifically designed for current transformers. So it's a similar family because it's designed for testing transformers. However, this is for testing power transformers, whereas that one is for testing current transformers specifically. Transformer oil tester, almost every power transformer is submerged in oil, and these devices can test the quality of that oil state and detect any failures which might be developing. And some protective relay testers and a number of other equipment we do, but that just gives you a rough idea how the products may look like and what they are. What are the links between Megger and Cardiff University? There were a number of projects in the past, and some of them I believe are still ongoing with a high voltage group and earthing measurements specifically, and also there were various magnetic aspects and research done with Professor Moses and Dr. Hall on current transformers. This is partially the reason why I'm here, that some of that research was done at Wollaston Centre. Some double clamp methods, which I will explain in detail what is this double clamp method, magnetic shielding and magnetic computer modeling. Okay, so let's just go to the topic of today's lecture, which is what is a current transformer? Current transformer is just a transformer. It is just designed in a specific way. So if we assume that is an ideal transformer, there are no losses involved and other things, we can say that the ratio of voltages between primary and secondary side is the same as the ratio of number of turns for the two windings. Of course, if we need to observe the conservation of energy, then it would be opposite for the currents. If the voltage goes up, current has to go down to have the same amount of energy. Hence, the ratio of currents is inversely proportional to the ratio of turns. So we can rearrange that equation, and we will get that our secondary current is proportional to the primary current with whatever the turns of the ratio is, the ratio of turns. And if we make our transformer such that is only one primary turn, we can take it out of the equation, and then we can see that the secondary current will be just directly proportional to the number of turns and the primary current. And that's what current transformer is. In many cases, is a transformer which has a single primary turn. Not always, but in general, we can simplify just to grasp the concept. However, in real life, Nothing is ideal, and we have losses, and we have other things which have to be taken into account. That's sort of very simplified equivalent circuit of a current transformer. We are still using that. Our primary has just one turn, secondary has multiple turns. There has to be some load connected to our transformer to measure voltage across, and we have some losses represented by our resistance of the core. And if we look at the currents and the values and the vectors of what happens, we will roughly get that the total current supply to the current transformer will be a combination of what we see at the secondary side times the number of divided by number of turns. So now it has to be multiplied to be transferred to the primary side, and the magnetization current, which sort of takes into account the inductance of the primary and the losses. So our aim is to what? To relate our secondary current to the primary current. So these would be almost equal to each other if our magnetization current is much smaller than our secondary current transferred to the primary or the main current, as it were. Where we can achieve this, we have to have conditions in which the impedance of our resistor here and our coil is much larger than everything else, and so that means a low loss of our core and very high permeability, and then we will get the condition where our secondary current times the number of turns is almost equal to the primary. This just means errors, and the question is how big errors we can accept.